All right, so guys, we're going to get rolling. So our Unit 3 is about transcendental functions, and I know that that word is sometimes a little bit unfamiliar. So typical transcendental functions would be things like e to the x, natural log of x, other exponentials, arcsine, arctangent, and I think I mentioned last time that we're going to look at some transcendental functions that you probably never heard of before, hyperbolic sine, hyperbolic cosine, which are basically variations on e to the x, some combinations of things. So we'll look at those a little bit later on. But we've done derivatives with a lot of other things, polynomials and sine and cosine and tangent, so on and so forth. And this is kind of our next step as we move forward. So in the video, you saw a little bit about the natural log function, the definition of it. A lot of times in calculus, you learn where things come from. For example, the volume formulas that you learned in geometry, like the volume of a sphere is 4/3 pi r cubed. No one made that up. It's from calculus. Even the area formula for a circle, area equals pi r squared. It's not like Pythagoras was like, I decree that this is the area formula, or somebody like that. It's calculus. It's almost all calculus. Anyways, so that's kind of the root of natural log. It comes from a definite integral from 1 to x of 1 over t dt. And you learned a little bit about the derivatives of those. And then the first example you saw there on the video involved the natural log of 5x squared plus x. So I thought what we could do here is do some examples, see how much the veterans in here remember, and see how much our non-veterans picked up from the video. And let's just do this. Let's go 2 through 5. Let's see if you guys can handle those. We'll go through some answers here in a little bit. Just see how much you're remembering, and if there's some things we need to fix or shake the rust off of, we certainly can. But I'm hoping that a lot of these are things that you can do, and we'll try it out. Okay? Ready to go. I'll be around to help. Hope it went really well. The basic plot is the derivative of ln of something, whatever that something is. The derivative of that would be 1 over something times the derivative of that something. Make sense? I hope I'm not overusing the word something there. I just want to be very general. That makes sense. So when you look at the derivative of natural log of 3x squared, that's going to equal 1 over the input, so 1 over 3x squared. But then, as always, the chain rule is always with us. You're going to multiply by the derivative of whatever that inside was, so times 6x. And, of course, you could clean that up quite a bit. Just ends up being 2 over x, I guess, right? Or 2x to the negative 1. Do I need to put a plus c on the end of that? Why not? Yeah, I'm differentiating. I'm not finding an anti-group. So, yeah. Okay. Any suggestions on number 3? So overall, you're right. Overall, it's a chain rule. And with a chain rule, it's always good to identify the inside and the outside. Wouldn't you guys say that the inside is natural log of x? The outside is 2 to the 6th. So what rule do you use to differentiate something to the 6th? The power rule. So our first step here would be to write 6 times the input all to the 5th power. But then we've got to multiply by the derivative of that inside. And the derivative of the inside in this case would be 1 over x. And so if you wanted to, you could just put over x. Or you could put times 1 over x. It's the same thing. So you could do this as well. Like so. Okay. How's this going? Remembering okay, veterans? Jeff? Jaden? How you guys doing? Doing okay? All right. So then number 3, the overall rule was a chain rule. For number 4, what's kind of the big concept rule? Product, right? It's something times something else. And so we're going to have to use the 1d2 plus 2d1 idea. So 1 is x to the 4th. d2 is 1 over x plus 2 would be natural log of x times d1 is 4x cubed. Clearly, you can clean that up quite a bit, or at least a little bit. That would be a fine answer right there. Look like this. You could just cancel those out and maybe go here. You could go overboard with cleaning it up. You could say that it's really this. You might see this sometimes. You could factor out that common factor. I would say that all of these responses would be just fine. No problem. You guys have any questions? Okay. And finally, number 5. This is the derivative of the natural log of x squared, right? So a little bit more of a complicated chain rule. You've got something inside something, and that's inside something else. So I'm kind of wondering what you guys think. What would be the first link in your chain rule? Yep, there you go. Times the derivative of the next inside piece. 1 over x squared times 2x. You guys good with that last piece for number 5? 3 links in the chain because there are 3 functions being nested together. So really, number 5 is a chain rule question. The details involve natural log. Question, Dylan?
So since you're taking a derivative of 1 over ln x squared, which...
No, we're not taking a derivative of that.
Okay.
So, like the way that I would look at this, how do I want to split this up? Like I'll just use colors. So my initial derivative is of just natural log of something, right? So let me fill this in like so. So I know that the derivative of natural log of something, and I don't really care what the something is, I know it's going to be 1 over whatever that something is. So that's natural log of this. And so the derivative of natural log of this will be 1 over this. Now, as I move inside to the next size box, or the next most inside function, it's the derivative of ln of something. It's not the derivative of 1 over ln of something. It sounds like you're wanting to differentiate this to get the next link in the chain. And that's not what we're doing. We're actually differentiating this right here. And so once again, the derivative of natural log is 1 over whatever the input is. And so as I differentiate just this part, it would be times 1 over x squared, because the derivative of ln of x squared is 1 over x squared. And then lastly, I would look at the most inside and say, well, what's the derivative of that? 2x. So don't think of the next link in the chain as being the derivative of the previous link, because the previous link is the derivative of something else. And we're always going to go back to our original expression that we're finding the derivative of to find the next link in the chain.
Yeah.
Does that make sense?
Yeah.
Okay. Great question. Anybody else? Okay, awesome. So then I think there's a little thing about logarithmic differentiation in here somewhere. There is, and there's that. Okay, cool. So let's see here. Yeah, let's do this. I'm going to show you this. I don't often show people this, but I think we've got a moment here to do this. Logarithmic differentiation, I don't think AB veterans saw this either. This is a totally optional skill. I don't think there are any questions on any of my tests or any questions on the AP test for that matter that require you to use this, but this is potentially a useful thing. Let me explain why it's potentially useful. If you take a quick look at what y equals on this one, you can see clearly there's a quotient involved, right? There's something over something else. But then not only is there a quotient rule involved, you see how when you did d high there would be, although simplistic, there would be a chain rule. And in the denominator there would also be a chain rule. So when you start to get these somewhat complex combinations of functions within something you're finding the derivative of, sometimes, and this could certainly be debated, sometimes logarithmic differentiation is the right choice. So here's how this works. If you wanted to use logarithmic differentiation, you would set this up by, first of all, doing the natural log of both sides. So it'd be ln of this, ln of that. Okay, so we're just going to go ln of both sides. Now, whether this is the right choice for you or not sort of depends on how good you are at those log rules. If you're good at all those little log laws, this might actually be a pretty nice technique. If you're not so good at the log rules, this would be a bad technique. Okay? So let's think this over. The left side is just going to remain ln of y, but the right side is natural log of a quotient. How do you expand the natural log of a quotient? Like what operation? Subtraction, yeah, it's minus. Yeah, exactly. So this would be ln of x minus 2 squared minus natural log of, I'll write this as x squared plus 1 to the 1/2. So all I did is I just took that expression on the right and I expanded it using log rules. Does that make sense? And then there's one more log rule we could use that we could use to expand to make this even easier. Yeah, bring down. You're right, exactly. So it'd be natural log of y equals 2 times ln of x minus 2 minus 1/2 of ln of x squared plus 1. once you have fully expanded this logarithmic expression, now the derivatives are pretty straightforward for the most part. So if you look at it, we're just going to differentiate. We're going to do d dx, because we're looking for dy dx here, or y prime. We're going to do d dx of everything. So d dx of ln of y would be 1 over y times dy dx, as we do this implicitly. So 1 over y times dy dx. And then the derivative of that first term, what do you think that would be? d dx of 2 ln of x minus 2? 2 over x minus 2, yeah. The derivative of the inside is just a 1, so we don't have to write that really. And then how about the derivative, the d dx of that next term? Yeah, exactly. So there's going to be some canceling here. 1 over x squared plus 1 is in there. You got to multiply by 2x. The 2 and the 1/2 will cancel. So then what I would do here, I'll step this out a little bit here. So I've still got 1 over y times dy dx is equal to 2 over x minus 2 minus x over x squared plus 1. The goal is to find dy dx. You see how if I just multiply both sides by y, the dy dx would be by itself?
To find it in terms of x.
But then you got to find it in terms of x. So if I wrote it out like this, I've got a good derivative here, but it's just not in the right form because it's got to be the derivative with respect to x. So I want that y to be something with an x. And if I remember to the very start, I know exactly what y equals, don't I? So then dy dx equals x minus 2 squared over the square root x squared plus 1 times this whole expression we already found. And yes, bless you, that is certainly an uglier looking form, right? But remember, the goal wasn't to simplify y. The goal was to find the slope of the tangent of y, and apparently that's what it is. So earlier I said it's highly debatable as to whether this is better or not. And I think the more complicated this original expression gets, perhaps the more likely it is that logarithmic is the better method. You could certainly look at this and be like, no, I don't think that's better. And I can say, all right, you're entitled to your opinion, and I might agree with you on this specific one. Others, perhaps, maybe you would actually think that this is better. If you know your log rules, not bad. If you don't know your log rules, bad, I would say. So something to think about. Yeah, Brandon.
Did you say we won't be tested on this?
So what I said was there is not going to be any question on an AP test or any of the quizzes or tests that I might give that requires you to use this.
But it could help.
It could, and I use that term in the most literal sense. It might help you, or it might not. You choose. You choose what works best for you. Just another tool in the toolbox. Choose to use it or don't. Yeah. But not required. Any questions or anything? If for those of you, and I can appreciate the fact that there are certainly some of you in here that, like me, would love to see connect things and make sure things are really equal. So, if you are interested, if you're sitting there and you've studied and you're good to go and you want some more math to do, you could do. This would be an interesting experiment. I haven't done it with this one, to be honest. Couldn't you just use the quotient chain combo that I mentioned at the start? Right? Because couldn't you just treat this like a quotient rule and with some chain rules in there? If you did it that way, you're going to get something that looks very different from what we got. But they would be equal. It would be interesting to see if you could take them and prove that they really are equal by using algebra, essentially. So, something to think about. A little challenge. A little algebra challenge. So, anyway. We're good? I want to show you guys something. I showed my veterans last year. I don't know if everybody has seen this or not. So I want to just read this to you. You can kind of read along with me. It says, because natural log is undefined for negative numbers. And I put that in there as just sort of an assumption that you know that. You guys know that you can't do ln of a negative. What else can't you do natural log of? 0, yeah. Natural log of 0 is undefined as well. So because of the fact you can't do natural log for for negative inputs, it creates an undefined output. We'll often see ln of natural log of u, ln of absolute value of u. The cool thing about this is we can actually differentiate the natural log of the absolute value of u as if the absolute values weren't even there. Yeah. So in other words, if you see, I'll show you the quick answer here, and then I'll prove to you perhaps that it's right. If you see the, f of x here, and you were supposed to find f prime, this is unique to natural log here. You could just say, well, hey, you know what? F prime is equal to 1 over the input, and you could just write it as 1 over cosine. And then you'd multiply by the derivative of the inside, which would be negative sine. And so then, of course, this would end up being negative tangent. And so someone who's thinking here is going to be like, whoa, hold on. Where did the absolute values go, right? Because in most cases in math, you can't just be like, oh, those symbols there, they just disappeared, and no big deal. No reason for that. Just whatever. No big deal. It is a big deal. So what I thought I would do here is show you that you can differentiate this as if the absolute values really weren't there. Here's how this works. If we take this off to the side here and kind of redefine what the absolute value of cosine really means. So absolute value of cosine is equal to cosine as long as what is true?
Either above x-axis.
Yeah, so I'll say if cosine of x is positive, right? So you can just successfully drop the absolute values as long as the input's positive. But if cosine of x, which it does sometimes, goes negative, what's the absolute value of that then?
The inverse of cosine of?
Not the inverse.
Or the negative?
The negative of it, right? The opposite of it. So negative cosine of x. So then, you can really look at an absolute value as being a piecewise. Almost in every case, you can say, hey, absolute value, there's basically a couple pieces. There's parts where the absolute values made a difference, and there are parts where the absolute values didn't make a difference, and that's what I've done here. So what if I then said, all right, so then f of x equals natural log of cosine of x, I'll just put that in parentheses, or f of x equals natural log of negative cosine of x, depending on the appropriate parts of the range, right? Range for cosine. Depending on whether cosine is positive or negative, we're going to have those two parts. Does that make sense? So let's differentiate them and see what happens. So f prime equals, over here, so it would be 1 over cosine of x times negative sine of x, just like we said at the start. And so that equals negative tangent of x. So then we got this other part. Well, what if it's where cosine is negative, and so we have to do the opposite of it? Right, exactly. So f prime of x equals 1 over negative cosine. And this is the part where you're like, oh, this is going to be totally different. But wait, what's the derivative of negative cosine? That's right, so positive sine. And so then positive sine over negative cosine is still negative, and it's negative tangent. So it's the same thing. So this is definitely unique to natural log as far as this pattern goes. But if you got the natural log of absolute value of something, you can just differentiate it as if the absolute values weren't even there. And this is why. No matter how you do it, it's going to work out similarly. Is that okay? Okay, fair enough. So that's it for derivatives of natural logs. This is a kind of a nice combination of sections here to do together. And this next section is 5.2. This section basically is what if you do integrals or antiderivatives that result in natural log. Basically the plot here. So if you watch the intro video, you've seen that we're looking for this pattern right here. Integral of u prime over u. And so for Jeff, for Jaden, this is the first time, more or less, that when we see an integrand that's a fraction, we don't like freak out and try to turn it into something that's not a fraction. Right? Up to this point, if we saw a fractional integrand, we're like, whoa, stop. We need to flip something up. We need to change something here because we don't know how to handle fractions as integrands. This is kind of the first time that we say, hey, we can actually do something with this. And there will be other times, too, where we can do things with fractional integrands. So that first example was given there in the video. I'm thinking, let's do one of these together, and then I'll turn you loose on the other ones here. There will certainly be chain rules involved, and Timmy messing up the chain rule or u substitution. That's going to be mixed in here as well. I thought we could do number 2. And here would be my thought process. I'll try to build this holistically, like from a big picture perspective. Say with number 2, if you approach this on a quiz or a test, it's out of context, you don't know where it's coming from, and you see a fraction as an integrand. Here would be my first thought that I want you to think about. If you see a fractional integrand, ask yourself this question. is the derivative of the bottom the same thing as the top? So you'd look at this and you'd say, all right, there's the denominator. Is the derivative of tangent the same as the numerator? And the answer in this case is absolutely. Yeah, the derivative of tangent is secant squared. And so if you can say, yes, the derivative of the denominator is the same thing as the numerator, then this is the very definition of natural log. And so here you would say this equals the natural log of the absolute value of tangent of x plus c. Those absolute values really should be there to account for the possibility of having a negative value for tangent of x, which of course, as we know, happens. Tangent does have negative outputs. Don't forget the plus c, because we are talking about antiderivatives, and that would be it. Okay? If you haven't already looked at numbers 3 and 4 and 5, I don't know if there's a 6 in here. Please do. Is there a 6? I don't know. 3, 4, 5. Can I just peek over your shoulder real quick? Yeah, let's. So I think you're going to find 5 and 6 to be a little bit different. Let's try to run through as many of these as we can. 3 and 4 for sure. If you think you can handle 5 and 6, give those a shot. 5 and 6 require a little bit of extra effort on the front end. But at least do 3 and 4. Ready to go. So let's check out number 3 and 4. So number 3. So again, I personally think it's valuable to think about this out of context and ask yourself, what would I do with number 3 if I just saw this on some quiz? I'm supposed to know what to do. You see a fraction, and the first question I think you should ask yourself when you see a fractional integrand is the derivative of the denominator the same thing as the numerator? And you might even want to do some sort of a u substitution or just sort of an informal u substitution. You might even say u equals x squared plus 2x and du equals 2x plus 2. I personally am a fan of doing that mentally. I think those are easy enough derivatives. You probably could see this. Bottom line is the numerator is not, right? It's not the derivative of the denominator. But this, to me, would be a Timmy messed it up scenario. It's a slight little error on his part. He hasn't learned, unfortunately.
How is he so incapable?
I don't know. At least. No, more like 18, totally. So we're only off by a factor of 2, though, right? This is exactly what it should be if I multiply this by 2. And if I multiply the top by 2, I've got to multiply the outside by 1/2. This would then end up leading perfectly to a chain rule leading to natural log. And so the 1/2 does not go anywhere. The numerator just goes back to the denominator. We end up with natural log of x squared plus the absolute value of x squared plus 2x plus c as our antiderivative for number 3. Any questions on that one? Number 4 is similar. It's maybe a little bit more simple than number 3, but it is a similar idea. Again, you got a fraction. And by the way, just so Jeff, Jaden, perhaps others don't get into this total comfort zone here, there are plenty of other examples where the integrand is a fraction, but the answer does not lead to ln. Right? This is not the only possibility here. It's just what we're working on now. So realize these thoughts you certainly need to adapt as we look at other scenarios. So the derivative of the denominator is 3. The top is a 1. Once again, Timmy has messed this up. So if all I do is just multiply the top by 3, it perfectly fits the chain rule leading to natural log, but I've got to adjust by multiplying the outside by 1/3. Once I've done that, the 1/3 doesn't go anywhere. The antiderivative then would be natural log, absolute value of 3x plus 2 plus c. How could you check number 3 and 4? Yeah, find a derivative. Should end up working out to be the original integrand. Okay, anybody struggle at all with 5 and 6? Definitely presented some challenges. I'd love to give you guys a general idea here of what to do. So here's the general idea. For a question like number 5 or number 6, and I'll zoom in on 5 here in a second, but here's the general idea. And it's always dangerous to give a general idea because we probably could maybe find an exception or two. I don't know if we could find an exception here or not. If you've got a polynomial in the numerator and a polynomial in the denominator, and here's the key idea, if the degree of the top is bigger than the degree of the bottom, then you're going to have to do some sort of division to get this into the form that you want. It's going to make it a little bit easier. So, for example, number 5, please notice that the degree of the top is 2, the degree of the bottom is 1, and so that tells me that I've got to do some kind of division. And it's simple enough division. Maybe all we really do is we split up the numerator, or we flip the x up and distribute or something like that, since the denominator is just a monomial. Here'd be one example of what you could do. You could rewrite this as antiderivative of x squared over x plus 3x over x minus 7 over x dx. Just split it up. You can split a numerator up over the denominator. You're basically just reversing the get the common denominator and add thing here. When you do it that way, you get a cancellation in most of the terms. That would be x plus 3 minus 7 over x. And you got to admit, when you look at that, that looks a lot easier than the original, doesn't it? Now it's just a term-by-term proposition. So the antiderivative of x would be 1/2 x squared. The antiderivative of 3 would be plus 3x. And how about that last term? Minus 7 ln of x, ln of absolute value of x, yeah. So this is where natural log comes into play on this one. That's why we would put it in here. You kind of have to know that in order to handle an integrand like that. An alternative, if you wanted to see a little bit of a different algebra look here, couldn't you have rewritten like this, where it's antiderivative of x squared plus 3x minus 7 times x to the negative 1? You could have just flipped that x up and then distributed. That'll get you here. Which is the exact same place that we were before. So either one of those is perfectly acceptable. It's just a different way of looking at the algebra. Who really cares? As long as it's valid, I think we're good. Any questions? Okay. So then number 6 is a similar setup. How is number 6 significantly different from number 5? Binomial instead of a monomial. Yep, you're right. So that changes things a little bit. We can't just flip up. We were over here joking a second ago about like math crimes. Some examples of some really horrific math crimes. Again, I guess this is being recorded on video, so there's no escaping what I'm about to write. Somebody could write this and be like, hey, I'm going to flip up just like we did a second ago, and then be like, oh, it's a binomial. Now, nothing wrong yet, right? I have not made any errors. Like, oh, it's a binomial, so let's do this, x cubed minus 4x plus 7. And then they just do this horrible thing like this, and then they get this trinomial times a binomial thing. And I mean, we kind of joke about this, and it is kind of funny and silly, but I show you these things because I've seen stuff like this, where people get a little desperate with the algebra, right? And you start doing things that you would normally never do, and you're like, I think maybe that's right, and oh my gosh. Scary. So I would encourage you to not look at algebra as just sort of an inconvenient detail. Sometimes the algebra is the thing, right? Sometimes that's the thing that's going to make a difference between success and failure. So please be careful. As you're doing your WebAssign, as you're practicing, you're working through and studying for a quiz or a test, don't look at it. Have you ever been guilty of this? Where you go through and you do something, and you get to a certain point and you say to yourself, and the rest is just algebra. And you quit. You know what I'm talking about? Sometimes, and the rest is just algebra, maybe that's the thing that's going to trip you up. So my point is follow through. Take it all the way through to the end, and you might find, yeah, you know what, the algebra was pretty easy. Or you might find, oh man, I'm glad I looked at this because I don't know if I remember how to do the algebra. And then you look at it and you get it figured out eventually, and you're like, okay, now I'm good. If I hadn't done that, I don't think I would be good. So I encourage you to do it that way. What do I have to use here? I do have to do division. Say again? Synthetic is a good choice. You could also do long division. Because the bottom is linear, it's really easy to do synthetic division. So I like that idea. But you got to be careful with this on the synthetic division. What do you have to be careful of? Yeah, missing degree on the top. Yeah. So for synthetic division, what you do is you put the opposite of the number in the denominator, so -2 instead of +2. And then you just string out the coefficients of the numerator. So it's 1x cubed, 0x squared, minus 4x plus 7. So you just string it out there to the right. Leave a little bit of space and put a line. This is how I usually do synthetic division. I think this is fairly standard. What's your first step? Yeah, bring that 1 right on down. And then now we start kind of the cycle of synthetic division. What do I do here to get the cycle started? Multiply. Yeah, -2 times 1 is -2. And then vertically, what do? I add. Yep. So 0 plus -2 is -2. And then I just repeat, essentially. I multiply negative 2 times negative 2 is positive 4. When I add this time, I get 0. And then negative 2 times 0 is 0. Add, you get 7. And then, since you divided a cubic by a monomial, or a cubic by a linear, then the result should be what degree? Squared, yeah. So then I could translate this as the antiderivative of 1x squared minus 2x plus 0. And then how do I write that 7? Because I'm out of degrees, right? Yep, you just put it over that divisor. You just rebuild the polynomial based on those coefficients. So, of course, once you get to this step, I mean, would this be fair to say? Isn't the algebra maybe slightly the harder part here? Like handling that synthetic division? I mean, I'm not saying that it's like really, really difficult, but the details of that might outweigh the difficulties of doing the antiderivative of x squared, right? Certainly that's not beyond you guys at all. So as you do this, you would find your antiderivative to be 1/3 x cubed minus x squared. And then how about that last term? What would be the antiderivative there? 7. Absolute value of x plus 2. And then don't forget the plus c. At least from a time perspective, it took longer to do the synthetic division than it took to find the antiderivative. Jeff, question? Say again? Say again?
You don't need to use the synthetic.
You could use long division, but you've got to do some kind of division.
Just use like kind of like this.
Oh, you did.
Separating top.
Whoa, I got to look at this here. And then, okay, so I see you split it up like that, and obviously you factored out an x. Oh, and then you factored that, didn't you? So I would say the pattern you're seeing right there is probably unique to this question. I can't say that that's going to be a dependable method. That happened to work here because the numbers just worked out the way they did. If the divisor wasn't x plus 2, if it was x plus 1, that method wouldn't work at all. So I think that's definitely mathematically correct. I have no issues with that, but just know that this technique will always work. Your technique will sometimes work, but not always. Okay? Cool. I like that. I've never seen that. I'd never seen that pattern with this one before. It's very cool. Okay. I think there's one last one to talk about, and that has to do with area. So this is a little bit of a connection back to chapter 4. Yep, that is it. You guys can see no calculator allowed. It says find the area of the region bounded by that graph, the x-axis on the interval from 1 to 2. So you guys would try to figure this out. We've got about 10 minutes left. Let's take maybe 5 minutes of it, see what you can do with it, and we'll finish it up with an answer on this one. Slightly different approach here. I want to make sure you guys are all good on why the area works out the way that it works out. And then I want to leave you guys with a little, I don't know, maybe a little hook for later on this year, coming up pretty soon actually. If you were to look at the graph of y equals x squared plus 1 over x, it's got a vertical asymptote where? At x equals 0, yep. So this graph looks something like this. It's got a diagonal asymptote. So it looks something like that over here. And you got that vertical asymptote there at x equals 0. So this diagonal asymptote would be somewhere in there. That make sense? Okay. So I asked you guys to find the area between 1 and 2. And so we're just going to say that 1 is like right about here. Oops. 1 is here and 2 is over here somewhere. And so all we're really doing, if you think about this, the integral you'd set up, I walked around, peeked over shoulders, I saw this a lot. Integral of x squared plus 1 over x dx from 1 to 2. That's a great setup. And if you want to think about this, isn't this essentially the height of each representative rectangle that you could draw in there? And this right here is the base of each little representative rectangle. So when you think about area, all you're really doing is a definite integral of height times base. Just doing rectangles. Infinitely many of them. They're super duper skinny. That's all we're really doing. So did you guys do the real quick division and cancel out the x's as appropriate? So if you did that, you'd get the integral from 1 to 2 of x plus 1 over x dx. You want to do that because the degree of the top of the fraction is bigger than the degree of the bottom of the fraction. This would leave you here, 1/2 x squared plus natural log of x, evaluated from 1 to 2. So this would lead me to, I guess you plug in the 2, it would be 2 plus natural log of 2 minus 1/2 plus natural log of 1. The number one question as I walked around, it was asked of me 3 times, what's the natural log of 1? It's 0, right? Yeah, 0. So we want to be clear about that sort of thing. Of course, 2 minus 1/2 is 3/2. So it'd be 3/2 plus natural log of 2 for our final, most simple looking area. Any questions? Okay. So I would like to leave you guys with this final thought. I had to carefully design this. I had to carefully design this to avoid something on the graph. What did I successfully avoid? Well, negatives I'm not too concerned about, although it does say area, and so that it does get a little weird. But what else is going on around that? An asymptote. So what if the question I asked you was a bit different? What if instead of asking you to find the area between 1 and 2, what if I asked you, very nicely, to find the area between 0 and 2? So in other words, what if I move this boundary over to here, and I said I want to find the area from 0 to 2? What would be kind of your gut reaction to that? Infinite, right? You guys see why someone would just their instant reaction is oh, the area is infinity, so it's not really a real number, so there isn't really an area? Interesting thought here. The answer to that question, and of course, you understand why, right? Doesn't it seem like the area would just kind of keep going up that way? So you just would keep adding a little bit more each time, and it's it would never end, therefore infinity. In this exact case, in this particular case, if you said that area would be infinite, therefore not existing, you would be correct. But in other cases, you'd be wrong, even with a vertical asymptote. Even with a vertical asymptote, okay? And so when we get to chapter 8, which I believe will be unit 4, which I think is the next one, we're going to look at situations like this where we're going to find the area and maybe one or both of the boundaries backed up to a vertical or maybe a horizontal asymptote. How would that work? How could you possibly get something that exists even though there's an infinite discontinuity? That's where we'll go coming up next. So that's not for today. That's for another day. So have a wonderful day. See you guys later.
In the answer 7.